Hey 13 Diploma Kiddies, and welcome back to topic 17. This is part C. So this section of the topic is linking in Gibbs free energy to equilibrium systems. So we know that Gibbs free energy from our previous topic is calculated using enthalpy and entropy and using the absolute temperature, and that if you have a negative G, the reaction is spontaneous, and that means that it's going to proceed in the forwards direction. If you get a positive G, we know that it's non-spontaneous, and so now we can actually make a connection that if this one's spontaneous in the forwards direction, then a positive G is non-spontaneous, and therefore the backwards reaction would rather occur. And if we have a G of 0, this is when the reaction is at equilibrium. And so this is what I'm just telling you for the first time now, and we're going to show a lot on this as we go through. So change in G, just a reminder, is the work available from a system. Okay, the work available from a system, and we'll talk about that as well. So the change in G is calculated, as we do everything, by G products minus G reactants. And so at equilibrium, these are equal, but for most reactions that are spontaneous, that G will be negative. Okay, so the difference between products and reactants will be negative. And a reaction will be spontaneous in a direction that decreases that free energy. So let's just have a wee look. So here's an example of Gibbs free energy during a reaction. So if we've got Gibbs free energy as being the G of the products minus the G of the reactants, what you've got to imagine is at the beginning of a reaction, the total free energy of the reactants is greater than that of the products. Okay, and so lots of work is available. Okay, so this value here is going to be bigger than the products, and that's why G is negative and it proceeds, right? Because the reactants have a lot more free energy. Okay, so negative because this is bigger than this one because the reactants have got a lot of free energy. Now as the reaction proceeds, the free energy of the reactants decreases and the free energy of the products increases. So actually as the reaction proceeds, the reaction becomes effectively less spontaneous, or G becomes less negative because there's less work available, and that makes sense. There's less reactants because they've formed products. So when the free energies of both the reactants and the products are equal, then no more work can be done from the system, and the system is at equilibrium. So if we're linking this to a car battery, so we go back to the beginning here. So at the beginning, when your car battery is fully charged, okay, that's an example of when the reaction, there's a negative G for the reaction because the reactants have got a lot more free energy and they're available to do a lot of work. Okay, and as the reaction proceeds, so the battery starts forming products, okay, that negative G becomes less so, and that's because there are less reactants and there's less work available. And then finally, when there's no more work available, the free energies are the same between the reactants and products. The battery is then dead. Okay, I hope that makes sense. So now we're going to look at some crazy looking wee graphs here. Okay, so the first point to note is that it doesn't matter if a reaction starts with only reactants. So just have a look here. So down the bottom is reactants, and on this side is pure products. And you're going to see arrows going both ways. It's because we're talking about reversible reactions here, hopefully because you've clicked we're talking about equilibriums. That's what this whole topic is about. So if we start with purely reactants, so up here, okay, you can see that as the reaction proceeds, okay, the G is becoming less negative. The free energy is becoming less negative, okay? And then it comes up this side here to the G of the product. So here's the, okay, so there's the G of the reactants, G of the products. So it's the difference between the two. Or if we start with the products and we go this way, so we start going down that way, you can see here's the G of the products, and then that leads to G of the reactants. So it doesn't actually matter if you start an equilibrium reaction with reactants or only products. Total free energy always decreases, and you can see this dip here, okay? Because your products would get used up if you were starting with products, or up here your reactants get used up. Now what you'll see is that there is actually, because it goes in both directions, because it is an equilibrium reaction, there is a point where it reaches like a lull before it goes up the other way. And that there is actually the minimum free energy of the reaction. And the minimum free energy of the reaction is when you can see here the free energies are the same. And so this point here is where we've reached equilibrium. And so this is said to be the minimum free energy because we can't do anything else. The reaction's at equilibrium. So that's just a really important thing to note. Okay, so if we look here, as we go from reactants to products here, you can see the reactants are getting used up and forming products, and it's a negative G. Okay, and if we start from the products and we go down, less negative, but you can see here as we go down, the reaction's still negative G. So it doesn't matter which way, and the point at which the free energy is the lowest is the point of minimum free energy, and that's equilibrium. Okay, so the other thing to look at is this was coming down this way. If we try and put the reaction the opposite direction, so if you tried to reverse it, you'd see that it would be non-spontaneous to push it up this curve, and the same the other way, you'd get a positive G. Okay, so that's quite interesting. Cool, what else do I need to say? So the other thing, team, is that a decrease in free energy as a reaction proceeds, actually, we see that as being work done by the system. So there's lots of free energy at the beginning, the reaction does its thing, and then we start seeing a lot of work from that system, and that leads to an increase in entropy, because you'll remember that, a reaction that proceeds always tends towards an increase in entropy. So therefore, the system has its highest possible value of entropy when free energy is at its minimum. So because it goes like this, and that your entropy is increasing, this point here, which is actually the minimum free energy, and the equilibrium point is actually the point where your entropy is at its highest. Okay, so I hope that makes sense. So let's just keep going. So we can use G to predict the spontaneity of a reaction in the position of equilibrium. So a reaction with a value of G that is large and negative, we already know from previous work is spontaneous, okay? But the part that we can actually add in from looking at this graph here, you can see that this part here, a big difference, because we're looking at the difference between its products minus reactants. So this value here is large because there's a big gap. So a large gap here, a large negative G, spontaneous reaction, we know it's spontaneous, okay? This is when you have a higher proportion of products in your equilibrium mixture than reactants. And you can see that because you can see here's your equilibrium at this point where free energy is a minimum. And if this scale down the bottom is products versus reactants, you've got more products than you do reactants because it's closer towards the product line. Okay? Now the other way is if what this is, you haven't seen this graph, this is a different graph. This is showing a positive G. So you can see here, here's your curve like so. Okay? And you can see here that going up this way from reactants to products is a non-spontaneous because it's a positive G. And what you can actually see is that this value of G is large and positive. It's non-spontaneous, which we previously know, okay? And if you look here, the equilibrium mixture here of this one, the point where you have the lowest free energy, you can see that it's mostly reactants in the equilibrium mixture compared to mostly products. So this is what we can actually use now in our answers to know. So we've got two things that we previously knew, which was that if you have a negative G, a reaction is spontaneous. So we know that, but now we can link that negative G into what that means in terms of your species presence at equilibrium. So if this is equilibrium point, then a negative G will have more products than reactants. And if you have a positive G, which is a non-spontaneous reactant, that's more reactants than products. So we can actually calculate equilibrium constants by using experimental data, okay? And we use both, G for this, and we also can relate your Kc by looking at your G, gas constant, temperature, and ln K is the natural log of Kc, so it's just the log of Kc. So we can use this equation here. You don't need to know how it's derived, but we can use this equation to make calculations or predictions about the Kc. So let's just have a look here about what this equation is actually going to show us. So the first thing is that we know that if you have a negative G, it means that the reaction is spontaneous, and it means you'll get mostly products. Okay, now the next thing we know is that a positive G means that we'll have mostly reactants. This is what we just looked at. And then if you have a G of 0, well, that actually means that you have both similar amounts of both. So then the next thing I want to link in with you is this relationship to Kc. So we know if something is mainly products, Kc is always products over reactants. So therefore you've got, if you've got mainly products, your Kc must be relatively big, so we're going to say greater than 1. So this is all kind of linking in everything we've already previously learnt together. And therefore, if it's mostly reactants, it's going to be less than 1, and that means that if you've got an equilibrium mixture, the Kc will be 1. The part that you may not know, some of you may not be as good with logs, it just means that the log of your K would also be positive, the log of your K would also be negative, and the log of your K would be 0. And so we'll go through some problems. So here's a question here. So it's this one saying calculate Kc from Gibbs free energy. And this is quite useful to do if the reaction's super slow or if equilibrium concentrations are low. The one thing I'll make sure that you know is you need to know that the units of G, Gibbs free energy, must match the units of R, which is joules. Okay, so not kilojoules. That's the main thing there. Okay, so let's have a look here. The esterification process has a free energy of negative 4.8 kilojoules. Okay, calculate the equilibrium constant at 298. So here's the equation. This is given to you in section 1 of your data booklet. Okay, and so we're actually trying to calculate Kc. So we'll have to solve for ln Kc and then rearrange. So you've been given a G, and the first thing we need to do is turn that G into just joules, so it matches that R up here, okay? So we're going to times the negative 438 by 1,000 to make it just joules, okay? And then on this side, you've got your R, which is 8.31, and your temperature was 298. So once you've times these two together, you'll see it's 2478, and these together is obviously negative 3480. So if you divide one by the other, you get 1.77. So hopefully you can see how that's done. If you go e to the power of 1.77, which is reversing or getting rid of the ln, you'll end up with 5.9. So quite straightforward calculations. The only hard part, like you look up this in your equation in your data booklet, the only hard part is to make sure that this unit, instead of being kilojoules, is just joules. Okay, so this one here, guys, is calculate the Kc at 300 K for the oxidation of iron. So the oxidation of iron is one of the forms of rust, okay? So here's some data. This one, instead of just giving you G, okay, instead of giving you G, they've given you some information. They've given you an enthalpy and they've given you an entropy. So you can calculate, to start, you can calculate G by going H minus the change in T. They gave you the T times S. And so you'll notice that I've changed this joules to kilojoules to match the enthalpy up here. Okay, and you'll see that there's my answer of G of negative 43.1 kilojoules per mole. Now I'm actually going to pause this and I'll come back to this question actually in one more part of the video. Okay, thanks team.